Good morning, everyone. My name is Rob Lopez, and I'm the team leader for the Ocean Spray Food Firmness study. This is the team: Austin Baird, Matthias Kidding, Nick Orphan, and Samara Dolan. Many of you are probably already familiar with Ocean Spray. We're one of the world's largest grower-owned cooperatives, and we're based out of Middleborough, Lakeville, Massachusetts. We produce a wide variety of cranberry products, including juices, sauces, and dried fruits. We have 3 facilities in Massachusetts, including a receiving station in Carver, where I myself worked 4 seasons as a quality tech, an operations tech, and an administrator. This receiving station was the primary focus of our project. And now I'm going to hand it over to Austin to discuss our problem statement.
So the main problem that the receiving station analyzed and was giving us the task to solve was the cranberries were experiencing a certain amount of damage during each transition point or step during the receiving process. They realized that there was a direct correlation between product resulting in more structural compost as well as a reduction in quality of the finished product, which was grazing. So the objective of our student design project was to find out the largest contributor of damage that was occurring to the berries, as well as provide a cost-effective solution by the end of our project. So as I previously stated, we're going to go in and we're going to analyze the major transition points at Carver. By doing this, we're also going to grab samples before and after each transition point, and we're going to use the firm tech that was provided by Ocean Spray, which is basically a rotary table with divots in it. We were able to put samples in it, and then applied load was directly contacting the berry, and then we measured the deflection, which was given in grams per millimeter. So using the results of the records of this data, along with statistical tools such as t-tests, we were able to analyze significant areas of damage, which is the focal point of our project. When it passes to Matters to discuss the results of each transition point.
After conducting the firmness test, we used a t-test to find to identify statistically significant transitions, which are shown on the graph with a red line. And transition 2 to 3 showed the largest firmness drop, which accounts for 42% of the total firmness reduction. And transition 2 to 3 is our point of interest, and Nick will continue with the existing design of this transition.
So the transition we selected is basically it goes from an inclined belt down 3 feet to a horizontal belt. Now in this transition, it hits those 2 metal plates, which are hard steel, and creates a hard impact for the berries and creates damage. This equipment was built in the 1980s when products like craisins didn't exist. Back then, all berries were made into concentrate, so fruit firmness was not an issue to them. Now I'm going to hand it off to Samira to talk about the prototype testing.
So our prototype was tested at the Ocean Spray pilot plant, and it's a scale-sized incline model of both our prototype and the current set of fabricated. The angle velocity of the incline were made to match those in Carver, and the firmness results from the prototype were compared to the existing setup to establish change in damage caused. The image right here at the top is our scaled-down model of the conveyor belts, and this is at the Middleborough location. And the image below, this is the current transition that Ocean Spray has, and this is what we're looking to change. Now I'm going to pass it off to Matthias to go over.
Because we didn't have access to fresh fruit to test the prototype, we used 3 types of fruit that were available at the time, which are semi-fresh, which was stored in a warehouse for 6 months, and the store fresh, which we bought at the time of the experiment, and the frozen one, which was found at the pilot test facility. And the thing about the fruits that we used for this test was that they are poor quality and they did not behave as similar to fresh fruits. They showed a really huge variation, which is shown at one of the fruits that we used to conduct the test on the prototype with large error bars, as you can see. And the variation made our result lack any significance, but we did not make any conclusion of that because we needed more testing to do so. We did hypothesis testing by comparing the current design with the new design. So we started by formulating our null hypothesis, and alternate hypothesis. The null hypothesis basically represents what represents a result that is likely to happen, and in this case it would be the new design showing no improvements and improvement in firmness compared to the current design. And the alternate hypothesis represents the result that is least likely to happen, and that is the new design showing improvement in firmness compared to the current design. We used alpha 0.02, which is a standard, and we did a z-test, a one-tailed z-test to test our hypothesis. And using z-alpha, we found our rejection region, which is from 1.64 to infinity. We calculated our z-score for each of the fruits that we used, and all our z-scores shown at the z column show that the z-scores are also outside of the rejection region, which means that we accept the null hypothesis. So based off the pilot test data, our hypothesis concludes that there isn't enough evidence to conclude that the new design is better than the actual design. And Nick will continue with his final design.
So our final design is basically a PVC chute. The vinyl used is a USDA approved flexible material to create a softer impact for the berries. The berries should only hit the bottom, but if they arc over, they'll hit the top and the bottom, but it will still be much softer than the metal that it hit before. This vinyl is mounted to a stainless steel frame, which is then mounted to the existing transition, so there will be little modification needs to the existing setup. We added an angled part to the bottom of the chute to decrease the angle at which the berries hit the horizontal belt to further minimize the berry damage. Now Austin will talk about the challenges we faced.
So as expected, with every project, we were met with our fair share of challenges as well as constraints that we had to strictly follow. One of the biggest challenges that we had to face was the ocean spray availability. So they're in operation 3 months every year, specifically September to November, which is basically our fall semester. So during this time, the most fresh fruit was available to us, which is a huge contrast to our spring semester when it was time to do prototype testing. We only were left with 3 sample opportunities that Matt was already covered. One of them being long-term storage freshness, which was samples that were held at the warehouse for about 3 to 4 months. The second option was store-bought fruit, which you could just get at your local grocery store. And then lastly, frozen berries that were also at the warehouse, and then we thawed. Unfortunately, all 3 of these samples had a high raw percentage, as well as a lower initial firmness, which were 2 factors that affected the overall quality. So a more material constraint that we had with our design was it had to be food grade because we're dealing with cranberries, and it also had to be weather resistant, which means it couldn't be corrosive, and it also had to be able to withstand long exposure to UV rays. And a geometric constraint that we had was there was a diverter gate along the conveyor belt, so this restricted the length of the chute. So instead of having a long length of the slide, and that would only result in one area of impact, we had to stunt the length of this chute and reduce the angle so it was a lot more abrupt. This caused 2 areas of impact instead, but we used PVC, so there was still a reduction in the overall results. I'm going to hand it off to Samara for the schedule and budgeting of the project.
All right, so our project started back in September, and this started with team selection and industry research. And this was for us to get a grasp on the problem statement given to us by our sponsors, Ocean Spray. And like Jean mentioned earlier, we did receive kind of a vague problem statement. We were asked to go in blind and to find where and why were the fruit losing firmness throughout the process. So we went to the Carver, Massachusetts receiving station, and we picked out 11 transition areas. And as mentioned earlier, these are the areas that have the highest damage to the fruit. Once the receiving stations closed for the season, we did analysis on the 11 transitions, and we figured out which transition had the highest percentage drop in firmness. As mentioned earlier, this is the transition that we're changing. So we came up with 9 ideas on how to prove this alternative, and then we did a design matrix to figure out, all right, which one of these 9 ideas that we have as a team is the best to move forward with. We picked our design, we ordered materials, which is around, in the beginning of the second semester, we ordered materials, and we began to design and fabricate our design. We then did testing at the Ocean Spray pilot plant, and then we evaluated our testing, and then began to build our final product to give to Ocean Spray. Now going with the budget, Ocean Spray gave us $2,500 for this project. As you can tell from the budget sheet, from September to February, we actually were resourceful. We didn't have to use any of the funds for the engineering and design process, up until we need to buy materials for our final prototype, for the final product. For the prototype, we actually used surplus material given to us from Ocean Spray, but also our own personal supplies to build the prototype. And then for testing, we used existing equipment from Ocean Spray and their pilot plant, and so we didn't have to use any funds there. We just used most of the funds just to, for the materials for the final product. Now I'm going to pass it off to Rob to do the conclusions.
So, wrapping up. In the fall semester, we successfully went into the receiving station in Carver and conducted a fruit firmness study. We managed to identify and isolate the major causes of damage in the facility and selected the largest contributor for our re-engineering. In the spring semester, we went to the facility again, identified the transition, took all the necessary measurements, and began re-engineering. Our final product is cost-effective, it's cheap, and it's simple enough that the facility can implement it on their own without any outside contract. For a budget of $2,500, we were able to procure all the necessary raw materials, tools, and equipment to build full-size models of our prototype on all three of their lines. And while we do not have statistically significant data to back up our design, we do have our qualitative observations of the prototype testing, where the fruit did flow and had less impact on the material. Future steps that the company could take would include tackling the next largest sources of damage in the facility, which will also outline the graph that was covered in red. Beyond that, Ocean Spray could also go to the other receiving stations in the system, seek out similar transitions to the ones that we improved, and apply similar solutions. All they would have to do is remeasure it and then recut the material to adapt it to the other transitions. And finally, Ocean Spray could follow the roadmap we used in the fruit firmness study at all the other receiving stations to identify their major sources of damage and then start from scratch with an engineering solution. And lastly, we'd also like to say thank you, of course, first to our direct liaison at Ocean Spray, project engineer Ben Ryder. He's helped us from the beginning and guided us every step of the way, and we would never have been able to complete this without his help. We'd also like to thank our advisor, Professor Wenzen Wang, and our professor She Produce, along with many other employees at Ocean Spray, like the pilot plant, their supervisor Joe Boylo, and all their technicians, the Ocean Spray receiving station in Carver, the manager Bob Gerard, and supervisor Joe Vitello. And lastly, I'd like to personally thank Ocean Spray Director of Engineering Ryan Moriarty. I approached him almost 2 years ago with a proposal to sponsor a project, and without his commitment, we never could have got this far. Any questions?